All right, so today I'm going to be talking about electron domain geometry, and my name is Anne Marie. And so we have 5 types of electron domain geometries. So the first one I'm going to start with is linear. So let me write that down. All right, and then so for each electron domain geometry, it's gonna be represented with one molecule, and then I'm gonna be making the molecules out of toothpicks and gummy bears, since we are post-Halloween, and I do have lots of leftover gummy bears. So for the first molecule, we're gonna be starting off with BeH2, which is beryllium hydride. So I'm gonna write that down. So BeH2, and then I'm going to write down the name, and always in lowercase, beryllium hydride. And then we're going to figure out the total valence electrons. So this is going to be needed for our Lewis dot structure. So I do not have a periodic table readily available, so I'm just going to go off of what I know on top of my head. So beryllium is going to have 2 valence electrons because it's in the second group. And then hydrogen always has 1 valence electron because it's in that first group. So you're gonna do a little math equation. So you have 2 valence electrons from beryllium, and then hydrogen is in the formula or molecule, it's H2, so there's 2 hydrogens available. So you're gonna do plus 2 of the 1 valence electron hydrogens. Then that's going to equal 4 valence electrons. You're always going to add up everything that's readily available, which is going to give you that total of 4 valence electrons. And so then we're going to go to our Lewis dot structure. So we always want to start off with the central atom. Central atom is beryllium. Hydrogen can always make 1 bond only. So you're going to do hydrogen, hydrogen on the other side. This is a linear model, so this is going to be in a straight line. Hydrogen is always going to make 1 bond here, only 1 bond there. So you have 1, 2, 3, 4 for beryllium, and then 2 for hydrogen, but that's just 1 bond. And then this is our Lewis dot structure. And then I recreated this with gummy bears, and I don't really have too many colors of gummy bears, so some of the colors are representing different atoms, or elements, as I should say. So yeah, but this is my gummy bear for that. So this yellow one is going to be representing beryllium, and then these 2 red ones are going to be representing hydrogen. And the toothpick, the single toothpick represents a single bond. And then it's also linear, has kind of that flat shape. So yeah, I'm gonna put that right here. And then so for the electron domain geometry, it is linear. And then the molecular geometry, for linear it only has 1, which is linear still. The bond angle, 180 degrees. And then, so the next part, we're going to be working on that delta notation. And the polarity arrows. So, I'm just going to draw this again, our Lewis dot structure. And then I'm going to use different colors. So blue, it's going to represent the delta notations. So for delta negative, it is less electronegativity. For delta positive, it is more electronegativity. So you can find that out from the periodic table as well. But beryllium is going to be delta negative. Hydrogens are going to be delta negative. I'm not the best at drawing these. And then, so for the polarity arrows, these atoms are going to be trying to split. So you want to represent that with these arrows going out. And so a little explanation. So these bond dipoles or dipoles are equal. So these are going to cancel each other. So there's going to be no molecular polarity. So this is a non-polar. But these bonds are polar covalent bonds. So polar covalent and non-polar overall. And then so for the next topic, we're going to be talking about hybridization. So this is when we're just counting those electron domains. So that's just whatever has these electrons on it, equal amount. And so for this particular molecule, I kind of want to go a little bit deeper. Just help me understand as well. So one of the 2s electrons is going to be moved, or as I like to call it, promoted to an empty 2p orbital. So this is going to be resulting in a 2p hybridized molecule. So that 2p. So, and then you can also just be like 1 domain, 2 domain. So it's going to be that 2p hybridized. And then for the formal charges, I'm just going to show this on our Lewis dot structure up here, just because it's less busy. But for formal charge, which I always like to abbreviate with FC, so you're going to be taking your valence electrons, the ones that you originally started off with. So beryllium's going to have 2, hydrogen's going to have 1, and then you're going to subtract it with the actual electrons. So this is what's touching the atom. It has to be physically touching, so it'd be here, 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 and here. So, and that kind of just to separate that, I like to separate these so you know. So it's going to be, so for hydrogen you have 1, it's only 1 touching it, so you only want to look at this side. So that formal charge is going to be 0. For beryllium, you're going to do the same thing. So the actual is 2. Or the valence electrons is 2, and then the actual ones that are touching it is 2. Formal charge, 0. Hydrogen's the same one. We've already done that one, so the formal charge is 0. And that is it for our linear molecule. All right, so for our next one, we're going to be talking about trigonal planar. So this is our second electron domain geometry. Okay, so for this one, I picked the molecule NO3 negative, which is nitrate. So I wrote that name out here. The total number of valence electrons. So nitrogen is going to have 5 valence electrons. Oxygen is going to have 6 valence electrons, but we have 3 of them. So you're going to want to make sure that it's 3 times. And then one thing that you always want to make sure of, and you never want to forget, is this negative. So that means if it's a negative, then we add 1 valence electron, or not just an electron. So you want to set up your little math equations. You have 5 plus 6 times 3 plus 1, because we're adding that electron. That's going to give us 24 valence electrons. And then our Lewis dot structure. So this is, I just made sure that all of the rules are met. So we have the octet rule, and then we can't go above 24. We have a double bond and 2 single bonds. And then the last step that I want to add, and this is going to show that it is that negative ion, -1. So that's just represented as that. So you always want to put the parentheses and also the charge on that. And then so the electron domain geometry, like we said, was the trigonal planar. And then for the molecular geometry, that one has 2 choices, but this one is still the trigonal planar one. And then the bond angle is going to be 120 degrees. And then let's work on that delta notation and plus the polarity arrows. So I'm just going to draw this out again. And then just to save us time, I'm not going to do all of the electrons, but so for the sigma, or the deltas, I'm going to be doing delta negative for this one, delta negative, delta negative. And these arrows are pushing away. And then so for this, we have a polar covalent bond. And then for this one, so the bonds of NO3 are actually polar, but the NO3 negative is going to be not polar. So, and pretty much every contribution is canceled. So the whole thing total is not polar, even though the bonds itself of the NO3 without the negative is going to be polar, but the whole overall is not polar. And then so for the formal charges, like our last problem, we're going to be subtracting the valence electrons from the actual valence electrons. So what we're going to end up getting is a formal charge of 0, formal charge of -1, formal charge -1, formal charge of 1. So basically, you want all of your formal charges to add up to what you have here. If it doesn't, you did something wrong, but if it does, it is perfect. And then for this one, I did the gummy bear structure. So this is going to be, I think, a little bent this way, but it's kind of hard with the toothpicks and the gummy bears. But I did do the double bond, so that's why I have double toothpicks right here. And then we have the single bonds here. The green gummy bear is a nitrogen, and the reds are the oxygen. So yeah, that is the trigonal planar. All right, so for the next electron domain geometry, we're going to be talking about tetrahedral. All right, and then the molecule that I'm going to be using to represent this is CH4, which is methane. For the total valence electrons, carbon has 4, hydrogen has 1, as we saw in other problems. But always remember to see this little guy, and that means that there's 4 hydrogens. So we're going to set up that math problem again. So 4 plus 1 times 4 is 8 total valence electrons. We're going to use that for our Lewis dot. So central atom is carbon. Then we have the hydrogen. So we're going to have 1, 2, 3, 4. And remember, hydrogen only makes 1 bond. So 1, 1, 1, 1. Super, super easy. So moving on, we're going to do the electron domain geometry, which we already said, which is tetrahedral. The molecular geometry at the same time is tetrahedral. There are 3 options for tetrahedral, but this one's just easy. And then the bond angle is going to be 109.5 degrees. And then let's work on that delta notation and polarity arrows. So for this one, there's actually no delta notation or polarity arrows because this is nonpolar. We had other nonpolar ones, but this one is just a little special. So we're gonna skip that step. So basically the bond between carbon and hydrogen does not have a great enough electronegativity difference. So these bonds are non-polar. So the whole molecule itself is non-polar. And then so for the hybridization, so there's going to be 4 electron domains. 1, 2, 3, 4. So this means CH4 is sp3 hybridized. And then so for the formal charges, I'm going to represent it up here. But for the formal charges of all the hydrogens is going to be 0. 0, 0, 0, 0. And then the carbon as well is going to have a formal charge of 0. And then I made my little gummy bear model. So this is going to be representing carbon, and then these are going to be the hydrogens. So we have 1, 2, 3, 4. It's going to kind of look like a teepee kind of thing. But yeah, then that's going to be it standing up. And then that's it for CH4. And then I did want to mention one more thing I did forget for the trigonal planar. For the hybridization, this is going to have 3 electron domains. So we're going to look at 1, 2, 3. And so this is going to be sp2 hybridized. Sorry about that. All right, so I'm going to be talking about our 4th electron domain geometry group, and that's trigonal pyramidal. For our molecule, I'm going to be talking about SbF5, and that is antimony pentafluoride. Super long, but super fun. So the total amount of valence electrons. So antimony has 5 valence electrons. Fluoride has 7 valence electrons. So we want to look how many there are. So we're going to times it by 5. And then we're going to set up our math equation. So 5 plus 7 times 5 is a grand total of 40 valence electrons for this structure. And so for our Lewis dot, what we're going to do is put that antimony as our central atom and then kind of follow that shape. And then we're going to do 1, 2, 3, fluorides all around. Kind of did that drawing backwards, but then we're going to start with our little electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Once you've checked that everything is right according to our rules, I went ahead and created the little gummy bear structure. So this is going to be that antimony, and then these are going to be all of the surrounding fluorides. So really fun, it's a really fun structure. So I'm going to just set that over here, a little reference. And then so for the molecular geometry, I chose the trigonal bipyramidal. This is that shape. And then for the bond angle, we have 90 degrees and 120 degrees. So let's do the delta notation and the polarity arrows. I'm going to take my little pen over here. So for that delta, we're going to have delta negative. Oops, don't know what that was. Delta negative, delta negative, delta negatives, and delta negatives. So this again means that it has less electronegativity than that antimony. Antimony is going to have delta positive. Then these arrows are going to be going out. So they're pushing away. Pushing away, and keep pushing away. All right. So overall, this is polar covalent. And then it is nonpolar. And then so for the hybridization, we're going to have 5 electron domains. We have 1, 2, 3, 4, 5. So that is going to equate to sp3d. So this is an sp3d hybridized molecule. And then for the formal charges, super easy, like we've been doing. For fluoride, we have the amount of 7 electrons to start with, but the actual electrons is 7. So that formal charge is going to be 0. And then for my fluorides, we begin with the 5 electron. Sorry, I totally went that backwards. So for antimony, we're going to have 5 valence electrons, and then what it's touching is going to be 5. So we're going to have 5 minus 5, and it's going to have that 0. And then for fluoride, we have the 7 valence electrons to start off with. 7 is going to be touching it, so we're going to have formal charges of zeros, 0, 0, 0, all around. And then that is SbF5. All right, so for our last electron domain geometry group, we have octahedral. So this one is going to have the most amount of molecular geometry options. And then for the molecule that I chose, we have SiF6 with a -2 charge. So what this is going to be is silicon hexafluoride. All right, so the total amount of valence electrons, silicon has 4, fluoride has 7, but we have 6 of them. Remember, like one of our examples before, we're always going to want to pay attention to this charge. So this means that we're gaining 2 electrons. So altogether, 4 plus 7 times 6 plus 2 is 48 valence electrons in total. So let's draw that Lewis dot structure. So this one is going to be a doozy. So we have silicon in the middle, and then we have this kind of fanning out shape. Fluorides, want to make sure that we have 6 of them. Bond, bond, bond. 1, 2, 3, 4, 5, 6. So we're gonna just repeat that all around. And then, like we had that one last time, we're going to make sure that this represents that negative charge. So parentheses go around the whole thing with that negative charge represented. And then for the electron domain geometry, we do have that octahedral. And then for the molecular geometry, it is still octahedral. So this has several options, but this one is going to be that octahedral. And I built this one. All right, so this one's probably the hardest one to build. It has the most components. But we have 6 of these fluorides surrounded by 1 silicon in the middle. So it's super fun. It's almost like pointing this way. Some of these start to droop, but yeah, it's really fun. It goes all the way around. All right. And so for this one, the bond angle is going to be 90 degrees. All right. So for this silicon is going to have that delta plus, and then these fluorides, delta negative. So it's going to be this fluoride. And it's going to be pushing out. All right. So the silicon hexafluoride has an asymmetric distribution around this central atom. So this molecule is actually going to be polar. And this is a polar covalent bond. Perfect. And then so for the hybridization, there's going to be, we have lots of them. We have 6 electron domains. 1, 2, 3, 4, 5, 6. So this is going to be the sp3d3 hybridized. And then so for the formal charges, basically like what we've done with all the other ones, silicon is going to start off with 4 valence electrons minus the actual valence electrons that are touching it, which is 6. So that is going to give us a formal charge of -2. And then these fluorides are going to have those valence electrons of 7, and then actually touching it is going to be 7 as well. So that's going to give us a formal charge of 0. And again, how you know that that is correct is that when you put these two together, they're going to equal that -2 charge. So everything's perfect. And this is our last one for octahedral. Thank you so much.